Questions about the logistics? Yes. We have extra class accounts. At this moment, contact the TAs because I have handed them over to them. We should have plenty. I don't think we have run out of them, but I don't have. We talked about some of the basic metrics in designing it. Talked about the yield and the cost of ICs, and we started introducing voltage transfer characteristics. What am I going to go over today are that is covered in chapter 1. We'll talk about the brief introduction to CMOS inverter operation, just a brief introduction in chapter 3. And if I have time, which likely may not happen, I'll try to do an overview. I'd like you to read for the next 1222 and 331 to 332, because that stuff over the manufacturing stuff I'll go relatively quickly. CMOS inverter stuff you've seen in E40. Relatively quickly over it. Again, I'll cover every point. It may be a little fast. Where we stopped last time when we ran out of time. Talked about the noise margins in digital circuits. A gate, and let it be as simple as an inverter. Looks like this. Inverter receives, in the first example, a beautiful, nice waveform that goes from 0 to VDD. What should it produce at the output? It should produce a beautiful, nice waveform that is exactly inverted, that goes from VDD to 0. It's something that looks like this. So here is my ideal ground, and here is my ideal VDD. You get something that looks like this. Out to the output. Something that is exactly inverted, noisy version of that? Or would you like it to clean up the noise? We'd like it to clean up the noise so that we get things that look digital. We'd like it to make exactly what he has done before. All in the labs and so on. There's the key difference. Try to preserve this. What does this do? What's the key property that does that? Well, the key property is that there is some kind of a threshold over here. time it gets something that is at the input. Is, bigger than VM at the input, solid 0 at the output. Something that is less than VM, it will produce a solid VDD at the output. Okay? So it will, and it's easy, right? Every time, it may happen that you'll add noise as you're going from gate to gate. Are the properties, how do we measure how well does it reject the noise, or how much is it immune to noise? Well, there are many metrics. The first one that is simple to introduce is, this gate should have, this is approximately where we stopped, went for a few more minutes, really would have an ideal characteristic that looks like that. It's a brick wall. Levels, and there is nothing in between. There is no transition level in between. Noise always is interpreted either as Vin, as a 0, or as a VDD. Levels that correspond to the output voltages, like V output high and V output L. Put a number of these inverters in a cascade like this. One driving another. This guy will be producing outputs that correspond to V output high and V output L at its outputs. So the next guy in the chain, the next inverter in the chain, will be seeing V output low and V output high at its inputs, and will produce voltage transfer characteristics should be unique. We'll see some circuits that generally, it should give you one-to-one relationship between what is at the input to what is at the output. Now, how much can we tolerate of a noise? The simplest metric is something that we have introduced at the end of it. What we have said is that we would like to identify these 3 regions in that would give us this, if these are structured, this natural rejection of noise and rejection. In order to have 2 regions with gains that are less than 0, we better have a region, right? Because we have to somehow get from we have to have a region with high gain. The higher the gain, the better. The less of a transition region we have. Okay. Very simple. And that's what we have talked about. Just to remind you, when people have gates that have very high gain, when they have this nice characteristics, it's easy to design digital circuits because we can put And there is beautiful thing that is called CMOS that we're using today as voltage transfer characteristics that look like this. Now people are talking about CMOS alternatives. There is bad news about CMOS alternatives. Many of them don't have. Size can be made to be smaller than a CMOS inverter, significantly smaller in scale, 5 nanometer barriers that people have been talking about, or 7 nanometer barriers. Can they be digital in a way that they not only it has to be smaller, we gotta be able to put 100 billion of them together. Otherwise, if you have to design something where you have to check 100 billion of voltage transfer characteristics, that's going to take a while. So the way how we introduce noise margins, we identify these regions where the slope is. So, well, the slope is less than. Put in at the input of this gate that has the voltage is higher than the input high is good, because that noise is going to be attenuated and is going to noise margin is essentially a difference between output high, this nominal level that comes out of here, and how much can we tolerate down to that point. So if you look at that, talking about two different noise margins in this moment. We'll refine this a little bit. So I'm just introduced two noise margins. Noise margin to logic 0, noise margin to logic 1. I can talk about different noise margins a little bit later. Question here is, should we be rejecting the noise? If this V output high, as labeled here, less than VDD, and then there is some VDD over here. About this noise going up? Well, probably not at this moment. In some other circumstances, I may care about it, but it's an interesting question. Well, it comes up in some other aspects as we'll see it. If you make output than VDD, you'll introduce noise, and you usually don't want to do that. Really, what you want to have this narrow, undefined region between. why do I care about noise? I mean, where does noise come from in integrated circuits? Start with. Why do I have noise? I mean, I get noise from the outside, but let's talk about electronic noise. Thermal noise. Is that the worst thing that can happen to digital circuits? It exists there, but it's not the worst thing usually. We've talked a little bit about the noise, the typical decoupling noise. Telegraph noise is another interesting phenomenon, but it's for a general, typical, well-behaved digital circuit. Random telegraph noise is not that big of an issue. It's an issue for typical places where the noise comes from is the supply voltage or coupling noise from another gate that is switching. We've talked a little bit about that. I've found out what is my noise margin that is going to flip the gate. That tells me how much noise can I tolerate. Can I estimate is my amount of noise that I have in the gate? More than that, I'm going to be in trouble. If it is less than that, I should be safe. Or lecture 3 approximation. So how can I guess how much noise is out there? Hard to guess it. You'll find out that we'll typically, we found out what will be the noise margin that we have. We have some amount of noise margin. We'll try to allocate some of those, and we'll try to keep these main culprits under their budget. So we'll find out that they'll tolerate the supply noise that is up to about 5% of VDD, and you'll get the target by your management team, or if you become a manager one day, you'll give your designers a target that you have to keep the supply noise less than 5% of VDD. We go to tolerating 15 millivolts of supply noise, and so on. There are noise sources that are proportional to the supply or to the signal level. There are noise sources that are proportional to the supply. How about supply noise? Usually proportional to the supply, a large component of it. Random telegraph noise, interesting you mentioned. Is it proportional to the supply or not? Now some of you asked, what is random telegraph noise? Anybody knows what is random telegraph noise? Those of you who have heard about analog stuff, it's called 1 over F noise. Anybody heard of 1 over F noise? So analog people know it as something that is called 1 over F noise, but if you haven't heard about it, it basically happens to transistors. This is slight digression, so I'll keep it very short since it's been brought up. It happens that as carriers travel through a transistor, they get stuck occasionally here and there into some imperfections. What happens if an electron is traveling through an NMOS transistor and gets stuck in the oxide? What happens to the threshold? Depending how lucky you are, and it gets unstuck and continues. IDS under constant bias changes. It becomes a little bit more, a little bit less. It looks like a telegraph. you get really unlucky, it can happen that there can be tens of millivolts and then off some of your noise margins. It rarely happens, but it can happen. That's one of the things. It's a popular thing of research these days. You hear a lot about it in conferences because it freaks out SRAM. And your nice SRAM cell is nicely sitting out there, is perfectly remembering that it was storing a 1 or a 0. It comes a little bit of a random telegraph noise event and throws off your SRAM cell. And or well, Venetian, for example, flash memories. Now, absolute noise margins are, one metric, but it's not the only one. And I do not intend to quantify that at this moment. Later, when I introduce many other things, we'll come back to it. Talk about the impact of noise. It's not just the absolute value of the noise margin that matters, right? Certain amount of noise. Is every single node in the circuit going to respond exactly? Types of capacitances, yeah. How about impedance? So if the noise comes out, we call it the general thing. Different types of capacitance, we'll give it a name. We call it impedance. Fair enough. So if the noise is voltage noise, will it like to sink into high impedance or into low impedance? What if it is current? If the noise comes in the form of current, will it like to go into? So you will see differences, depending on what. Now, the challenge there, I'm just giving you a flavor. Now imagine your $100 billion transistor chip has, several hundreds of billions of nodes that all have different. Property like that. It has low gain, high gain in between, and low gain when the input reaches high. We'll put a bunch of them next to each other. I'll put some value here, V0. Let's say that V0 is not really at logic levels. It is in between 0 and VDD. So here is my V0. I happen to V0 to produce V1. So I'm going to go across this VTC, and I'll find V1 over here. Output of this VTC produces V1. This is the output voltage, right? This is input-output voltage transfer characteristic. Now, what is the voltage transfer characteristic of the second inverter? Well, I can overlay it on top of this one, right? You know, now my input becomes the y-axis. You know, V1 is the input to it. X-axis becomes the, now I can overlay the output axis over the x-axis. So what I'm going to have is a VTC that looks like that. V1 is going to produce a new output that is V2. Then it's going to go through a normal VTC here, and it's going to make something that is V3 that is have a different type of transfer characteristic where the gain is not at the right place. Put a V naught here, and even that if that V naught is very close to the VDD, so V naught close to VDD, it's going to produce V1. One is going to produce V2 that is close to the middle, V3. All of the other inverters that I put down that look like this are going to have outputs that are equal to logic levels. No, all of them are going to be somewhere in between. Is that a good gain? Is that a good gate? No. Want characteristics that look like that. Very soon we'll see direct applications of this. So, you know, in general, a simple illustration of that is you want a regenerative property. All logic levels. There are a few other properties that we would like to talk about. One of them is fan out has two different definitions. There is a conventional definition and more modern that applies only to CMOS. Simple definition of fan in. Simple definition of fan out is the number of gates that it drives. Different definition that goes like this. You calculate what is the, or measure what is the input capacitance here. You measure what's the capacitance at the output and the fan out. Fortunately, this is how it has been. You know, two different terms, one term used for two different phenomena. I'll be more often using this one because it directly applies for calculating. The other simple thing is the fan-in. What is the fan-in? Well, it's the number of logic inputs that the gate has. What is the fan-in for an inverter? 1. Or gate 3. Simple. Now, the ideal gate, we can already say that what we would like to have as a gate is something that has 0 gain here, output resistance, it can drive an infinitely large fan out, and it's old-fashioned inverter. This is an inverter from when I took an equivalent of 141. Voltage transfer characteristic would not reach VDD. Have some gain, but that gain would not be, really great. Let's talk about what is, what are the properties of this gate. We have, and I'm having issues with fonts, obviously, but that is not going to distract us. So, by applying the output of one gate to the other that is identical in the chain, I'll find out what are the values of the output high and the output low. So I'll find out by overlaying this whole thing, if I want to do that. I'll find out what are my values of output low, V output high. I'll find where the gain is here. Gain points of 1 are here and there. This would be V input high. Where is my V input low? It'll be over here. Noise margin is the difference, low noise margin is the difference between V input low and V output low. The noise margin high is the difference between V output high and V input high. And I can easily calculate those. So they are spelled out on the over here. The other thing is this, that we care about are the delay definition. That's a very important thing, right? We would like to find out how quickly this gate can switch. Put a bunch of them together in a path, how quickly we can get the signal from the input of the path to its output. We put registers at the end, something that you might have seen in CS61C. Find that path and find out at what is the maximum frequency that we can run that gate, or that path. Remember, we would like to run these things at a few gigahertz if we can. So it's very important to know what is the propagation delay of each of these gates. How do we calculate propagation delays? I mean, we have waveforms that look at the input something like that. Adopt a convention, and that convention says this, that propagation calculated from 50% to 50%. 50% of VDD rising waveform to 50% of VDD. Propagation delay is defined with respect to the output waveform. So that's why I have high to low. My output is going from high to low. Propagation delay is defined as 50% from the point where calculated as the time that it takes for the gate to go from this point to that point. LH is defined equivalently for the low to high transition at the output. It's the point from where the input reaches. Why 50%? Why of VDD? Why not of V output high? That's correct. But there is a more important, slightly more important thing. Yes. That is correct, right? I mean, fundamentally, I want to find a propagation delay of a chain of gates. Their propagation delay is better not being dependent on if they have different V output highs and V output lows, they better not be dependent. Better have it defined to something that we can just add up. Now, when you open a catalog nowadays that gives propagation delay, that talks about the technology and what, say open book for the 32 nanometer technology or 45 nanometer technology, you'll find out that the delays are sometimes defined at 40% of VDD, sometimes defined at 45% of VDD. Hard to find the one where it's 50% of VDD. That mean? Well, that is true, but why? I just want to tell you this so you don't get surprised when this is actually a trick question. So I just want to see how you think about it. So what you'll find out is this thing happening. Have a waveform take this at, say, 40% of VDD. I'll call this TP high-low, right? Because the output waveform is the one that goes from high to low. A valid definition. Am I at liberty to pick any points that I like? As long as they're consistent, right? I can pick anything I want. I can pick 5%, 10%, 20%, 30%, 40, 50. Third gate coming up. So I have H for the second gate. every single textbook uses 50%, but the catalogs use 40 or 45 or something like that. That's a very good observation. But why do they do that? Yeah, because you open up an application manual for a technology and they pick 40%. And you gave the right answer. Why did they do that? Good idea. So we merged these two answers. What does it say about this technology? Propagation delays from high to low and low to high do not have to necessarily be equal. Why are they not going to be equal? Because of the nature. Because of the way how we have designed things. And we'll find out why we do that. For the convenience, nothing wrong is going to happen if TPLH is different than TPHL. It's just going to be more convenient if we make them approximately equal, and I can eyeball all the delays. Find 5 gates, add 5 propagation delays. I don't have to add 2 TPHLs and 2 TPLHs and so on. Why? Because I mean, the gist of his answer is we would like to make TPLH be equal to TPHL, approximately equal, for no physical reasons, just convenience reasons. Well, it will turn out that in some cases it happens at 40% of VTT. When we talk about the propagation delay, for a gate, we'll say it's approximately average of TPHL plus T. Why do we? Does this average have any physical? Do you ever see this average propagation delay in when you're trying to time the path? No, you only see TPHLs and TPLHs. But why do you care about the TP? Yeah, exactly. So when somebody asks you, what is the propagation delay of an inverter in this process? Oh, TPHL is this, TPLH is that. People would like to say, I give you one number, the average. Although it's not something. But in practice, what you're going to find out when you're timing a path that has inverting gates, you're going to see approximately. Propagates into a 1. That 1 becomes a 0 here. One switch to a 0, the 0 to 1, 1. Evaluate characteristic of a new process. Whenever they publish, they've developed this kind of process, they'll publish as well. They'll measure they'll lay out the ring oscillator, and from the ring oscillator they'll get a average propagation delay for an inverter. It's easy. You know, how long does it take for this zero to loop around? How many propagation delays? So it's going to go through this inverter. It'll be one low to high, high to low, low to high, high to low, low to high, high to low, low to high. Go through, if there is 5 of these gates, we'll go 5 times through low to highs, 5 times through high to low transitions, until it gets back to the first value. All the period of this ring oscillator is going to be equal to 2 times the average propagation delay times the number of stages. Or it is equal to the n times. Other than that, propagation delay has no meaning. Average propagation delay has no meaning. Because we will always, when we time the path, as you will see from this class, what do you care about? From the standpoint, how fast can you run this whole thing? What is the worst case propagation delay? Does not. So say you have 2 different propagation delays. Once when you put a 0 at the input, the other one. The 2 different propagation delays, right, through a path. Slightly different. Run your chip at the average frequency of those 2. How often your chip is going to be working correctly? 50% of the time, which is not usually what you want. What is the timing that you need to apply to that chip? The worst case, the worst of the 2. What we'll find out is this. The output of a gate behaves as switch the input of one gate, I get the RC response. So, to draw that, time domain looks like this. I can draw it for the purpose of illustration. Step at 0, going to voltage V. My output is going to look like this. Have the output waveform that asymptotically reaches the value of V. In fact, waveform here is given by this. Enough times in E40 that I don't have to do it here or wherever you now in the simple circuit is equal to, by the way, how we have defined it before, our propagation delay here at this output from low to high well, what is the delay until this point, this waveform reaches? Or approximately 0.7 times RC. So propagation delay of a simple RC gate, 50% point is 0. What is TPHL? I've drawn TPLH here. What is TPHL value? Now, I would suggest you to remember this right away because we are going to be using it a lot. Most of these problems will be reduced to solving a first-order differential equation and finding a propagation delay that comes out of the first. Do I solve every time this differential equation, or can I just apply the result? I know, I still know how to solve the first order ones. Output of this waveform. So you asked me what is V out. V out was the output. Find out in just 15 minutes that this is pretty well approximates how an inverter responds to a waveform. Why do we like this? Because it approximates delay not only of an inverter, it approximates well logic gate in CMOS. Okay, power dissipation. Now, power dissipation is not as easy. Somebody asks you, what's the power dissipation of this phone? What would you tell them? Or what's the power dissipation of a and nobody has a laptop on. What's the power dissipation of a processor in your laptop? What do you answer? 30 watt. 15 watts. You'll find out that they're typically sitting somewhere over there. But what kind of power is it? Is it when, what's the power of a processor here? What is it dissipating now? The 40 watt processor in here. What is its dissipation? Is it 40 watts now? No. But it's not 0. It is less than 40 watts because it's running PowerPoint, and I'm actually doing exactly nothing in this moment. All it is doing is refreshing the. But if I run Spice, which I occasionally do, believe it or not, it can heat up. I mean, it can run up to 40 watts. What does that mean? It's the maximum power. But there are many types of maximum power as well. Have you heard of what are the different? So there is maximum design power. There is some other type of power that is larger than that maximum power. Have you heard of power viruses? Power viruses. Okay, so maximum design power is what design team designs for the practically shortest loop, that the worst case loop that is going to exercise that processor the most, is going to make it. Mean people that have made power viruses. Those are viruses that do not do anything useful. They just run such a tight short loop in an application that a processor beyond the thermal design point, the maximum point. And they've been able to burn some process. That was in older times. Now there is the next power that is hopefully larger than that is the thermal design point. What is the highest temperature that it can tolerate that corresponds to some power? And there are thermometers and stuff like that that will say, okay, now you're getting too hot, we're going to shut you down. There is average power. Average power is typically much less than the maximum power. Otherwise, it will be pretty bad if you're always running at maximum power when you're doing nothing. What you're going to find out, there are many types of power that we're going to see. There are a few of them that are of interest to us. I'm going to define the instantaneous power. Instantaneous power is I take the current voltage and the current value of the current, multiply the two, and I get voltage is, if we ignore all the noise and everything, if the voltage is equal to VDD, that is equal to product of the supply voltage and the instantaneous power, or the maximum power. Here, power is equal to the V supply times I peak. That is usually different than the maximum power. Why do people care about the maximum power that corresponds to the maximum current draw? Yes? Break your device. Well, let's use a little bit, you're absolutely correct. Let's just use a little bit more of a technical term. Burn your supply voltage or whatever that current comes to. Because that current may be so, that event of drawing the peak current may be so short, it's not going to heat up the device, but may burn your supply. And then you're going to find the average power, which is the amount of power dissipated during a certain amount of time. Find the T any way you like. T can be running an application. our virus, running time, and etc. There are a few other things that people do. So we've heard that the power is really important nowadays, but the performance is also important. We usually, the faster they run, that means they have less of a delay. So how about if we try to get the best of both worlds? We would like to have the maximum performance and the minimum power. Like to have then that without say that they're completely that there is some unknown relationship between them. I want maximum performance, that means minimum delay, and I want the minimum power. Therefore, in order to get that, I can try to minimize the power delay product. But if I say I multiply the average power and the propagation delay, what do I get? How can I minimize or take forever to switch? They'll give me a minimum of the power delay product. Run things as slow as possible, like take a year to switch a transistor. Actually, you'll find out that people power delay product is not a good objective. You'll find out that people will try to one of the possible objectives. We'll see there are some better ones. So it used to be a very popular thing. There people are using something else, and you have it in a book a little bit written up about what else. Any questions about this? Nobody minimizes power delay product. Multi-core designs are minimizing why? To answer this, I give you an A for the class. You have another 30 seconds. Different kinds of metrics to express that. You might have heard of these things like MIPS per milliwatt and MIPS per. kind of concluded to some extent that energy and delay are related to each other. If you want to run things really at low energy, both energy and delay in the mix, you need to somehow find some kind of a trade-off. So that gives equal weight to energy and the delay. But that turns out not to be that desirable these days. We find out that we want to put a little bit more of a weight on the delay than on the energy. This is not something that is officially published, but most of the designs nowadays are going to be optimized. A harder question. It involves things that you have not learned in might have heard in other classes, especially if you're a graduate student. Why not ED cube? Because you'll find out that this is VDD invariant. Right? You know, when you plug in a processor, you don't know at which supply it runs. We'll come back to that a little bit later. This metric is supply invariant. Why? If you differentiate energy with supply, you'll find out that it's a power of 2. If you differentiate delay with respect to supply, it's a power of 2 minus. Nobody uses. It's just for the textbook purposes. Yes, Rachel. On faster than the propagation delay, generally. Power is going to be down faster than the propagation delay. If I have infinitely long propagation delay, it takes me a 0 power to do that, and I get to 0. How do I find what is the energy that takes a meter? Well, if I want to charge this capacitor, you know, move this value. Power times the time. The power is equal to VDD times the current that is being drawn out of the supply, IDD. Happens to the other half of the energy that is drawn from the supply, gets dissipated on this resistance. First one, can you do this simpler without using integrals? What's the charge that is stored in a capacitor? CV. Why is it 1/2 CV squared on the capacitor? Why does the resistor not matter? Why do I not have R anywhere in these equations? Doesn't store any energy. That's a kind of a experienced answer. Can you give me a little bit more intuitive answer? How what happens if I'm what are you saying if I make this resistor? Let's try to. Where is the energy dissipated then? I mean, I'm missing a half of the energy then. And I just claimed that a half of my energy gets dissipated on a resistor. Miraculous device. It has 0 resistance. When I close it, other half of CV squared. Capacitor leak. I mean, no. It's an ideal capacitor. Yes. That's how Hertz made his Hertz waves by doing that. Has to, energy balance has to be satisfied. This energy has to go somewhere. On Tuesday, story about the inverter.